Section 4.5 is applied max and min problems, okay? So we're going to look at what we learned in a previous section about finding an absolute max, absolute min, and we're going to apply it to real life problems. All right, so for the first two examples, we need to remember the area of a rectangle formula. Area is equal to length times width. All right, I think everybody remembers that. Well, let's look at the first example from our notes, okay? What does that first example read? Well, it reads, a rectangular field is to be bounded by a fence on three sides by a straight stream on the fourth side. Find the dimensions of the field with the maximum area that can be enclosed using 1,000 feet of fencing. All right, so I'm going to draw some kind of picture here, okay? Here's my straight stream. All right, now I'm going to enclose this pasture with fencing here, and fencing here, okay? And this will be the area of my pasture. Maybe my cattle or sheep or whatever I put in there will be fenced in by fence here, and they're not going to cross the stream, I'm assuming. All right, now, what does it want me to do? It wants me to find the dimensions of the field with the maximum area that can be enclosed using 1,000 feet of fencing. All right, so we need to find this length, and this length, the dimensions. This length is unknown, I'm going to call it X. This length is unknown, maybe I'll call it Y. Well, this length is the same as that length, so I'm going to call it Y as well, okay? All right, now what do I want to maximize? I want to maximize this area, because depending on the shape, we get different areas, even if we use the same amount of material. So if I want to maximize the area, I want to find the maximum of the area. We learned how to find maximums of stuff, and the stuff we found maximums of were regular functions. So let's find an area function. Let's find an equation for the area. We just said area of a rectangle is length times width. So X times Y. Now, how do you find a maximum? Take your derivative, you find your critical points, you evaluate your function at critical points, and so forth, right? Well, the problem here is that I have too many variables. I have X and Y. So I need to get this down to one variable here. So what I do is I use the other bit of information they give me, which they told me how much fencing I have, right? Let's talk about our fencing, okay? Do you agree that the fencing is going to cover this much, plus that much, plus that much? Or the fencing is going to cover a length of Y plus X plus Y. It's not going to go around the stream part. All right, how much fencing did they say we have to work with? They said we have 1,000 feet of fencing to work with. And I'm going to call this X plus 2Y if I have my Y's. Now let's solve this equation for Y. So we have 1,000 minus X is equal to 2Y. If I divide both sides by 2, I get 500 minus X over 2 is equal to Y. So what I'm going to do over here, instead of Y right here, I'm going to replace it with what Y is here. 500 minus X over 2. So A is equal to this X times, but instead of Y, we said we're going to use 500 minus X over 2. Now we're just down to an X variable over here. So this gives me A is equal to 500X minus X squared over 2. All right, now, how do I find the maximum of this? Well, I take the derivative and find the critical points. A prime in this case. A prime, or the derivative of A with respect to X, is 500 minus X to the first, right? Because remember that 2 gets multiplied here and 2 divided by 2. Now find your critical points. So take your derivative, set it equal to 0 or find where it's undefined. Actually do both. So I can set it equal to 0 but it's not going to be undefined anywhere. So I'm just going to get critical points from this. So x is equal to what? 500. All right, so I know what this x value is right here. I know this x is 500 feet of fencing. It goes right there. What do I still need? I still need how much goes on y. How much fencing goes on y? Well, isn't y equal to 500 minus x over 2? Y is equal to 500 minus x over 2. So if I know what x needs to be, I can sub it in right here. So y is equal to 500 minus 500 over 2. And if we calculate that, we get what? 250, right? So right here we need 250 feet. And right here we need 250 feet of fencing. It'll maximize my area. So let's see. Let me write out my answer. How am I going to write out my answer? I'm going to write out like something like, because let's assume that you're trying to, like you're going to be an engineer or something, and you're trying to tell somebody how to build something, because as an engineer, you design usually, and somebody else comes out and builds. Nobody's going to pay you an engineering salary to do construction. They're going to pay you engineering salary to do engineering work. All right, so I need to explain to somebody, how do I end up describing this for the builder? I'm going to say the two parallel sides need to be 250 feet each. Two parallel sides, 250 feet each. And the other side needs to be what? 500 feet. Now, you could either put your answer this way, or you could go ahead and put it this way on the figure. Probably on the figure would be the best, actually. But box it in. All right, let's look at the second example. Erase all this stuff and we'll look at the second example. All right, the second example reads, the manager of a department store wants to build a 600 square foot rectangular enclosure on the store's parking lot in order to display some equipment. I could draw a picture of that. I'm going to draw me a rectangle. I'm going to say this rectangle needs to be what? 600 square feet, it says. All right, three sides of the enclosure would be built of a fencing that costs $14 per running foot. The fourth side would be built of cement blocks that it costs $28 per running foot. Find the dimensions of the enclosure that will minimize the total cost of building materials. So I do not know what the length of this side is. I could call it X. Well, this is the same measurement, so I'm going to call it X. Do not know what this length is. Let's call it Y. Well, we could call this one Y as well, right? Now, three sides need to be built for $14 per running foot, and the fourth side is going to cost us $28 per running foot. So the more expensive side, I'm going to make one of these shorter sides to save me money, right? It doesn't matter which one. So I'm going to say this is the $28 per running foot side. And all other three sides, we're going to use the $14 per foot material. So my figure looks something like this. Now, what do they want me to find the max or the min of? They say, well, they don't ask me to actually find the max or the min, but they say find the dimensions of the enclosure that will minimize the total cost. So the function that I'm going to try to minimize is going to be cost. All right, now, there is no particular formula for cost, okay? It depends on what you're dealing with. So for this one, let's make up our own formula. How much is this going to cost me to build? It's going to cost me $14 per foot times X feet for that side anyway. $14 per foot times X feet. Plus the cost of this side. this side's going to cost me $28 times the number of feet right here, right? So 28 times y. And if I keep going along the same pattern, I have $14 per foot times x feet plus the cost of this side, $14 per foot times y feet. So cost, I'm just going to call capital C is equal to, let me combine terms here, I have 28x plus, what's that, 42y. So I want to look at finding a maximum, or I'm sorry, finding a minimum in this case. I don't want to maximize because I want to minimize. All right, so what do? I find a derivative, find my critical points. Well, it's going to be hard to find a derivative if I have two variables, right? So let's get it down to one variable. Well, what's the other bit of information they give me? Look back at your problem. What's the other bit of information they say? They say something like it needs to be 600 square feet, the area, right? What shape is this? A rectangle. So area will be length times width, right? So area, they're telling me, needs to be 600. So I'm going to fill in 600 for A. What do you want to call the length here? What did we label the length as? X times, what do we label the width as? Y. Now solve this equation for Y. So 600 over X is equal to Y. So instead of Y right here, I'm going to sub in 600 over X. So my cost will be 28X plus 42 times 600 over X. Now it's in terms of one variable. Well, let's see. I'll get C is equal to 28X plus, let's see, that's a 0, 0, so that's a 12, so that's a what? 25,200 over X. All right, now let's take our derivative here. C prime, derivative with respect to X is going to be 28 minus 25,200 over X squared. Instead of using a quotient rule right here, all I did was I did in my head, what if I bring X to the side? Then this term would be like 25,200 X to the negative 1, right? Then I thought, okay, negative 1 times this, I use the power rule, and that'll make that negative 2, and then we bring it to the bottom. If you're not comfortable doing that, use a quotient rule then. All right, how do I find my critical points? Find out where my derivative is equal to 0, and find out where my derivative is undefined. So let's take this derivative, 28 minus 25,200 x squared, set it equal to 0, and let's find out where it's undefined. It's going to be undefined where its denominator is equal to 0, isn't it? So if I solve this part here, I'm going to get x is equal to 0. Is that going to help me out any right here? Think about it. What does x stand for? The length of this side of my enclosure, right? So if x is 0, I don't have any width at all, and then I can't make a rectangle. So this doesn't make sense in the context of this problem. So let's solve this equation. If I multiply each term by x squared, I get 28x squared minus 25,200 is equal to 0. 28x squared is equal to 25,200. And then if I divide both sides by 28, what do I get? If I divide both sides by 28, I don't know what I get. I must get 900. So if I take the square root of both sides, I get x is equal to plus or minus 30. But if x is the length of a side, it can't be the minus 30. So I'm just going to use 30. X is equal to 30. So right here, I have each of these x's is 30 feet. This x is 30 feet. Now I need to find my what? My y's, right? To find my y, how do I do so? I use this fact, y is 600 over x. Y is equal to 600 over x. So y will equal to 600 over, what does x need to be? 30. So what does that make y? 20. So right here I'm going to have 20 feet for y, and I'm going to have 20 feet for y. And you can clearly see which one goes with which price, or which length goes with each price right here, okay? Because otherwise you got to word it kind of long and so forth. All right, so what did we do in each one of those problems? We found out what we were trying to minimize or maximize. Like this one, we're trying to minimize the cost. Then we had to get it down to what? One variable instead of two variables. How did we do that? We used the other bit of information we had, right? Got it down to one variable over here, and then took the derivative, find the critical points, and throw away the ones that do not make sense.